Hi, I'm Nevin. So the goal of this work is to make reinforcement learning agents safe and beneficial for humans. And to do this, I think agents should be rewarded for fulfilling human preferences. So some previous work that took a step in this direction is to use supervised learning to train a human preference predictor and use that as the reward signal for a reinforcement learning agent. So this predictor will output a high value if human preferences are fulfilled and people are happy, and a low value if they aren't. And this preference predictor was trained using human feedback for the training signal. So my goal is to make that human preference predictor for the reward generalize better. So to help with this, I think that a reinforcement learning agent acting in the real world will have to implicitly learn human preferences in order to do well. So I think that because humans make up a big part of the world, so in order for the agent to fulfill its reward, it will probably have to interact with a lot of humans. So I think that the agent will implicitly learn a model of human preferences in order to fulfill its reward well and interact with people more effectively. So a way that we can take advantage of that is to start training an agent with an initial reward function that doesn't have to be aligned with human preferences. And through the training process, I think that the agent will build up a model of human preferences. So then we can use a technique to extract those human preferences from the reinforcement learning agent, and then use that to create a human preference predictor that will make a better reward function for the agent. So we can apply this reward function back to the agent and continue the process if we want to. So the work that I'll talk about just focuses on the part of if you have a trained reinforcement learning agent, how do you extract human preferences from the agent that it learned? So the previous work has the human preference predictor take the raw state of the environment as input. But I think that in order to take advantage of what the reinforcement learning agent implicitly learns about human preferences, I think that we should use the hidden activations of the reinforcement learning agent to train the preference predictor off of. So I think that this will help because the reinforcement learning agent has visited a lot more states than we can collect human feedback for. So I think that through that process, the agent will have built up a much more complete and robust understanding of human preferences than we can get from the human feedback alone. So how that works with the Q-learning architecture is that we can take the hidden activations from one of the layers of the architecture and then use that as input to a neural network that is trained to predict human preferences. So this network can be trained with human feedback for a training signal, and it will be trained to predict a higher value if human preferences are fulfilled and a low value if they aren't. So the environment that I tested this on involves an agent that tries to collect apples in the environment. But if it collects too many of them, a simulated human gets angry and starts eating them to decrease the agent's reward. So the way for the agent to prevent this is to activate an electric fence, but that costs reward. So the agent has to figure out the right time to activate the electric fence by understanding if the human is angry or not. So in this way, the agent essentially has to develop a model of human preferences in order to do well. So I think even though the environment is really simple, this part where the agent has to have a model of human preferences in order to do well mirrors what happens in the real world. So notice that the agent is rewarded for collecting apples, which isn't actually aligned with human preferences. So if an agent can learn human preferences in this environment, it shows that it can learn them even if its reward function isn't actually aligned with human preferences. And hard-coded rules were used to generate the data for human preferences in this environment. So the results that I'll show are with 50 training examples because I wanted to see how well these techniques would do with a very small amount of data. So training off of the RL agent's activations that I talked about got 0.93 AUC. And then training off of the baseline methods did significantly worse. So training the preference predictor off of the raw image only got 0.8 AUC. And training off of an autoencoder that to autoencode the image did even worse than that. So the results showed that reinforcement learning agents implicitly learn human preferences, and also that training a human preference predictor off of the hidden activations of the RL agent does better than just training off of the raw state of the environment. So in the future, I want to try training the reinforcement learning agent using that preference predictor as the reward function, and also to improve upon the neural net to extract the preferences by trying other techniques that might work better.